Good evening, everyone, and welcome to the April meeting of the Ottawa Centre of the Royal Astronomical Society of Canada. I can scarcely believe it's April. If you didn't show me a calendar and I looked outside, I wouldn't believe it. We've got a pretty packed program tonight, so we'll try to wrap things up on time. We're going to start off with some of our usuals. Dave Chisholm with Ottawa Skies. Al Scott is going to be giving us our 10-minute astronomy news of the month. We've got a special guest tonight, Quinn Madsen from Carleton University, to show us, to give us a little bit of a talk on the program that he's in at Carleton and some of the projects that he's involved in. After the break, we're going to have Dr. Janet Tulloch back up the podium to give us her second part of her presentation, Outstanding Standing Stones. Then we'll close with observations, announcements, and door prizes. We actually have some door prizes this month, so be sure to grab a door prize ticket during the break. All right, members in the news, I'm going to ask Gordon to come up here for a second. And just go ahead and click it.
Which one, center one?
Right, to the right.
This one?
Yeah, that's the one.
Okay. So back at our annual dinner meeting, we award prizes or recognition for different things. And one of the things was Article of the Year. And I had selected Stuart Glenn, and he's conveniently made himself absent for the past few months. So we haven't been able to present him with this. His article was called The Hug, and I'm sure you all remember it, describing an event at one of the CARP star parties. And one of the joys of outreach was someone sharing their enthusiasm with him. Stuart? At last.
So much for passing on the parking lot.
There we go. Exactly. There's a little. Okay.
All right, thank you, Gordon, and thank you, Stuart, for your contribution to the newsletter. And I hope to see you earn a second prize at some point. All right, new members. This past month we had Alex Nielsen, Douglas O'Brien, and Stephen Simmons. Welcome to the club. And thus far, we've had 18 new members in 2019, so I hope you're all enjoying your membership. All right, and up next, I'm going to call Dave Chisholm up for his Ottawa Skies.
Okay, so let's see what's happening in the month of April. First of all, we've got the moon phases for the month. It's a new moon tonight. Full moon is on April the 19th. And that particular full moon is known as the Paschal full moon. It's the one that triggers Easter, which is the Sunday immediately following that full moon. We have the Lyrids meteor shower. And of course, the moon always cooperates for our meteor showers. We're going to have a waning gibbous moon on the best night for that, April 22nd and 23rd. So it'll wash out most of them, but after midnight in a dark location, you should be able to see them. They're expecting 20 meteors per hour at its peak. Mercury is not visible. Venus is visible just before sunrise. And Mars is visible the first part of the evening. The rise set times that you see on the screen here is on the first of the month and on the last of the month, just so you know. Jupiter is visible just before sunrise. Starting to move into the evening now as well. And I'm not moving.
You guys point to the booth.
There we go. Oops, I went too fast. Saturn is just visible before sunrise. Uranus is visible early evening all month, and Neptune is visible before sunrise the last half of the month. And there's our cartoon of the week. Thank you very much. Or cartoon of the month.
All right, thank you, Dave. All right, and up next, I'm going to call up Al Scott for his 10-minute astronomy news segment.
Good evening. As you can see, I'm pushing for warmer weather. So I got some interesting stuff for you tonight. First one is about Bennu. The OSIRIS-REx spacecraft is currently orbiting the small asteroid Bennu. Bennu is what is termed a rubble pile with a porous, sponge-like interior. However, its shape, especially the presence of a series of ridges that run from pole to pole, also indicates an internal stiffness that helps hold the asteroid together, at least for now. Bennu is about 525 meters in diameter, a bit wider than the Empire State Building, is tall, and it resembles a giant floating 10-sided die of the gods, thus the title. Currently, Bennu rotates with a period of 4.3 hours. So this is speeded up movie here. And its period is shortening by about a second every 100 years. This is due to something called the Yorp effect, which is due to sunlight pressure and uneven heating causing one side to push more photons off than the other side, and it actually speeds up the rotation over time. Big boulders cover Bennu's surface, many of them up to 10 meters in diameter, leaving few safe spots for the spacecraft to land later this year to collect samples. Researchers had classified Bennu as a primitive carbonaceous chondrite, many of which have water and carbon-based compounds on their surface. OSIRIS-REx has now taken spectra of the asteroid's surface, revealing hydrated minerals, as well as evidence of hydroxyls. These are molecules that contain hydrogen and oxygen atoms, potentially left over from water interacting with the rocks. Researchers think that these molecules are part of water-bearing clay materials, which point to a past interaction with water, most likely before Bennu broke off from a much larger parent asteroid sometime in the distant past. Bennu is one of the darkest objects in the solar system, consistent with the carbonaceous chondrites. It only reflects 4% of the incoming light, so this thing is black as tar, effectively. However, some parts of the rocky surface reflect up to 20% of the light, and this variability has been posing a challenge for the spacecraft's laser-based navigation system built in Canada, led by Professor Mike Daly of York University. This here is one of the potential landing sites that they've outlined on the surface of the planet, or planetesimal. Interestingly, this is not a breakfast cereal. OSIRIS-REx has witnessed the asteroid spew rocks and dust into space at irregular intervals. This view shows the asteroid ejecting particles from its surface on January 19th, and it's a composite of two images, one a short exposure of the main body, 1.4 milliseconds, another a 5-second exposure of the surroundings, showing the particles clearly. The first plume event was detected on January 6th, and since then the team has detected a total of 11 episodes. During an event, the asteroid may eject dozens or even hundreds of particles into the space around it. The particles range in size from centimeters to tens of centimeters in diameter. Most of these particles move slowly relative to the asteroid's escape velocity. So while some of them assume short-lived orbits that are expected to last a few weeks to maybe months, they eventually make their way to the asteroid's surface. A small percentage of the material escapes the asteroid's gravity. The debris these events leave behind could result in meteor showers visible from the Earth when our planet crosses Bennu's orbit in late September of every year. So this is really cool. You may see these particles later. My second item, this is a cool one from Japan. Every now and then a star appears to flicker out for a fraction of a second, its light blocked when a small object in the outer solar system passes in front of it. While some of these objects are large enough to be seen by reflected sunlight, most are far too small and distant and to be detected directly. So-called stellar occultations, where the light of a background star briefly winks out, are the only ways to know these objects exist. Basically, when their shadow passes over us, the shadow from a distant star being occulted. Astronomers using basically amateur equipment to monitor some 2,000 stars in a densely populated field down to visual magnitude 13, have discovered what appears to be a kilometer-sized Kuiper belt object. This is a missing link between the size of the dwarf planets and the many much smaller objects in the far-out Kuiper belt. So these astronomers monitored a star-rich field in the galactic plane located within about 2 degrees of the ecliptic to improve their odds of observing one of these stars blinking out. Astronomers at Mayaka Open Air School in Okinawa set up 2 identical observing systems on the roof of their building using off-the-shelf equipment. The 2 setups each included an 11-inch Celestron astrograph equipped with a ZWO ASI 1600 MMC CMOS camera, which ran at 15 Hertz frame rate on a Takahashi equatorial mount. Combined with a focal reducer, control computer, and data storage, the total cost of each system came to about $16,000, which is relatively inexpensive for professional research. The system was dubbed OASES, or Organized Auto Telescopes for Serendipitous Event Survey. So the reason they use 2 telescopes is that they're monitoring 2,000 stars at 15 Hertz, and some of them are very noisy. And you don't want to detect birds flying through your field or airplanes or things like that. You want to make sure things are blocking out both telescopes at the same time. You place them far enough apart that a bird isn't going to blink out the star in both telescopes at the same time, basically. They can also monitor all of the stars and look for just one star in the field blinking out. And what they do is they're looking for... reset. Speaking of blinking out... So they're looking for a coincidence event. Oh, we're back. So you can see here's the data of the brightness of one star in the 2 telescopes, the blue and the red traces, and this is the event that they observed. So you can see that the data is relatively noisy on its own. So by looking for coincidences, they're able to significantly increase the statistical likelihood that what they're seeing is a real object blinking out the background star. They used images of faint random meteorites to synchronize the 2 telescopes' frames very precisely. So when they saw these faint meteorites in both telescopes, they used that as a time reference to make the telescopes align in time. Observing for little over a year, the telescopes amassed 60 hours under good weather conditions over the course of about 13 months. Put in terms of observing hours per star in the field of view, OASES captured the equivalent of 60,500 star hours of data at 15 Hertz. So roughly 50 terabytes of data. Out of all this data, the team found a single coincident blip with statistical significance marking a candidate Kuiper object between 1.2 and 2.1 kilometers in diameter and radius. The fact that they were able to see one suggests that there is a very large population of these objects floating around in the Kuiper belt, and that there are a lot more yet to be discovered. And the sort of equipment that they're using suggests that anyone could do this. So it's a really cool experiment that you could try if you had, $16,000 or $25,000 worth of hardware. Oh yeah, easy. So that's all I had on the news. One other thing that you should be looking out for next week, there's been an announcement of press conferences, actually 6 simultaneous press conferences around the world by the Event Horizon Telescope team next week. And this team is using radio telescopes to try to image the event horizon of a mega black hole at the center of our galaxy. And so I think there's some interesting news coming out and probably a picture of a black hole next week to look at. So, yeah. So keep your eyes peeled. Thank you.
Okay, so it seems that little power surge that we had has knocked out the audio system. Chris, is that accurate?
We haven't figured out what the problem is yet after that little power failure.
All right, so we're gonna have to shout into the crowd here. All right, and with that, I'm gonna call up Quinn Madsen to give his talk. Quinn, you can advance the slide with this. If you need a pointer, it's this one.
Okay.
Advance pointer back.
All right, don't touch the bottom button.
Okay. Wow, I am completely overdressed for this. I was not aware. All right, so hello, my name is Quinn Madsen. I'm a fourth-year engineering student at Carleton studying aerospace engineering, specializing in space system design, which is just a mouthful. But what I am here to talk about is the project I'm working on, or I'm working with, the Carleton University Satellite Design Project, or CubeSat. And before we really get into it, I just want to take this chance to thank RASC for the opportunity to come in and speak. I've never done anything like this, and as far as I know, no one from CubeSat has. So this will hopefully be a bit of a learning experience for everyone. So first things first, I'm just going to go over really quickly what I'm going to be talking about. I'm going to be talking about our mission, our group, and our history first. I'm going to be getting into our mission statement and why exactly we picked the mission that we're working on. I'm going to talk about our satellite and exactly how the mission requirements shaped our satellite, as well as the layout of the actual system. And I'm finally going to give a little bit of a glimpse on how our design is progressing and what we're working on right now, and how future years are going to be working on it. So, who are we? Okay, point at the right place, I guess.
You gotta point up towards the booth.
Okay. No.
Maybe the bugs are getting us.
Maybe.
There it goes.
Couple of, there we go. All right, so who exactly are we? CubeSat is a team of 27 students this year from a bunch of different projects, from a bunch of different programs, and we're all working together to build a CubeSat. What sets us apart at Carleton is that we are actually a full fourth-year capstone project. So we have professors grading our work, we have volunteer lead engineers coming in guiding us, and we have the full support of the school. We've actually been at this, well, I haven't, but we have been at, the project has been at this for more than 20 years right now, making us the second oldest project at Carleton. You can actually kind of see me in the back right there. I'm currently a member of our payload team, and I've been spending most of the year working on a thermal camera, which has been a lot of fun. Now, we haven't actually been working on CubeSats for all that long. For most of the 20 years that this project has been going on, we have been working on, I keep saying we, I wasn't there for that. I wasn't alive for most of that, or a fair chunk of it anyway. It was mostly paper projects, designing communication satellites, Earth observation stuff, but nothing we would ever get to build because those things cost millions to billions of dollars to actually build and launch. About 3 years ago, with CubeSats becoming more common and launch costs lowering, it was realized that we could actually build something. So the project became to build a CubeSat and launch it. Now, even with launch costs dropping and CubeSats becoming pretty simple and easy to buy, it still costs a lot of money, something that not a lot of students can really afford right now. So we are working and competing in the CSDC, the Canadian Spacecraft Design Competition, and we're competing against other universities for the chance to actually launch our satellite. Now, what exactly is CSDC? Put simply, CSDC is it's a university competition for a bunch of teams. It can be capstone projects, clubs, or just a bunch of students working together. And the idea is to simulate as closely as possible the engineering industry experience. So CSDC itself, they work as the customer in this case, and every team has to work as a company competing for this contract. So we're sending in reports to them, we're sending in design reviews, we are giving them all the documentation we can so that hopefully we can win this thing. As far as requirements that they give us, the baseline requirements, the high-level stuff, they actually give us a lot of leeway. This is just some basic stuff for our CubeSat, mass requirements, size requirements, how long it has to be functioning, and power requirements, as well as some orbital stuff there. Now, I suppose it's time to actually get into what we're doing here with our project. Our mission statement is as follows: to discover anomalous hotspots for the purpose of determining the location of forest fires as a technology demonstration. So our project, our satellite, will sweep the boreal forests of Canada and send back images of thermal hotspots that our ground team could identify or reject as forest fires. If they find anything, they can alert the authorities in that area and hopefully catch it before it gets too big. Now, we could have done a whole lot of things with this project, but why did we pick what we picked? We picked it because forest fires cause massive damage every single year, and they wipe out huge swaths of forest. According to the Government of Canada, they burn down 2.5 million hectares a year, and they're caused by humans 55% of the time. A last little note there is causing damage if near populated areas. That was really the clincher for us whenever this was decided a few years ago, because we've found a couple of examples. The Fort McMurray fires did $9 billion in damages and displaced over 3,000 people. And this is a really good example of the damage if near populated areas, because they basically went straight through that town. BC is we've actually been working with the provincial government a little bit with this, because BC is at huge risk of forest fires. What you can see right here is the largest burn area ever recorded in BC, and it's big. It's just really big. And our last little example is the California wildfires, a little bit more recent. Only did $3 billion in damages, which is still a lot, but compared to the Fort McMurray, really shows you what the location can do. However, it did kill over 100 people, making it the deadliest wildfire in California history. So all this together, it really made us decide that this was what we wanted to work on, because the causes of these wildfires, lightning and mostly people, are not going to go away. However, if forest fires are caught early, they can be extinguished before they get too big, before they cause much damage. But they have to be identified first. Now, with our initial technology demonstrator, but also with plans for a constellation of satellites, we're hoping that we could actually catch some of these before they get too big, hopefully prevent something. Now, I'm going to go into our satellite and how it's built, how it's laid out. I don't know what kind of knowledge base we've got in the group here, but like most satellites, ours is composed of a bunch of different subsystems. You've got the satellite payload, you've got the thermal subsystem, the ADCS systems, structures, command and data handling, and you've got power. Now, what makes a CubeSat interesting and a little bit easier for us as students is that in most of these cases, the components are literally just stacked on top of each other in a giant sandwich and crammed inside of a little shell. And here we've got another view of the satellite, again showing how the boards are all going to be set up, the payload at the top with the camera, the antenna deployment stuff. And I mentioned earlier, the requirements mentioned earlier, that it had to be a 3U satellite. Now, with CubeSats, 3U means 3 units, and every unit is a 10 by 10 by 10 centimeter cube. So ours is just 3 of those stacked on top of each other, loaded up with all of our electronics. Also, as we can see here, the layout is dictated by our mission. Because this is technically an Earth observation satellite, we've got our camera up at the top. That's going to be pointing down at the Earth. Our ground station is down at the Earth, so we've got the antennas there as well. The GPS, however, that's going to be pointing back out at space, because we need to be able to access our GPS satellites out there. So now I'm actually going to get into some of our subsystems and explain how they work and the work that we've done on them. First up, because I'm biased, is my subsystem, which is payload. I will admit I am a little biased in this, but it is the most important subsystem. Because without this, you wouldn't have a mission. This is what is doing most of the work. Everything else is just there to support it, or that's just what I tell myself. So our subsystem, which you can see right over there, this is not flight hardware. This is just what we're testing with right now. We were provided a small thermal camera by a company out of Montreal called INO. Our structures team built a nice little telescope for it. And the entire payload system consists of that camera, a small thermoelectric cooler tucked in there to make sure that the actual camera optics don't get too warm or too cold, because that would ruin our image. And it will also have a small custom interface board because the camera currently outputs at video speeds and our computer can't handle that. So we need to build something, or we are building something that will throttle that image output a bit. Now, the thermal subsystem of a satellite is mostly concerned with just keeping everything in the Goldilocks zone, basically. Making sure every component is within their own temperature operating range. And it has a couple of ways of doing this. It's got passive heating, it's got passive cooling methods with radiators, it's got heaters spaced throughout the structure, and it also has reflective coatings here and there to avoid too much sunlight getting in. Most of the work this year from our thermal team has actually come from refining and streamlining a lot of our older simulations using Siemens NX and MATLAB. What we can actually, and as you can see here, they've actually managed to streamline this a lot, which really helps with our testing. They managed to get the number of nodes down by over half, which, considering the kind of testing I do, has been a godsend. Attitude Determination and Control, or ADCS, basically handles where the satellite is pointing and knowing where the satellite is pointing. And it has a couple of ways of doing that. First off, you've got photodiodes, or sun sensors, spaced around the satellite, and those will send an electrical signal if they see the sun, or a certain star if we pick a star sensor. We also have magnetometers that can actually tell where the satellite is and where it's pointing based on the Earth's magnetic field. And the team, the ADCS team, they throw all of that into an algorithm with what's called a Kalman filter. And at the end of all that, it spits out exactly where the satellite is in its orbit and exactly where it's pointing. It also spits out exactly where it needs to be pointing based on our target for that day. And to actually get it there, it has a couple of methods. It's got a couple of reaction wheels in there, which basically just spin to apply a torque and get the satellite pointing where it needs to. The structures team is basically, the structure of the satellite basically just protects and contains all the other subsystems, which, considering that this thing is going to be launched on top of a rocket, is critical. Poorly, as we saw in some of our earlier testing with vibration plates, poorly designed structures can literally shake themselves to pieces, which we definitely don't want happening on launch. A lot of the work this year from structures team has gone into completely redesigning our structure. This is one of the simulations they've got going right now, and they've been running it through, they've been putting it through its paces. All signs so far are that it is good to be built, which the rest of the team is definitely very happy for. So the command and data handling, or C&DH, is the brains of a satellite. Ours consists of a small off-the-shelf onboard computer, or OBC, that links every subsystem, handles and directs the flow of information through the satellite, and provides a link between the sensors and the software. Any information going anywhere on the satellite has to flow through the C&DH system, so their job has involved a lot of integration work with all the other teams, making sure everything plays nice together. All right, comms system. Our satellite only has a limited ability to store information, and it only has a limited window in which to actually transmit the data back to Earth. So for that reason, the communications team has picked a circularly polarized antenna in order to get all that data down as fast as possible. They've also developed a bit of a deployment mechanism for the antennas, because those can't be out during launch. The way it works is it uses burn wires. Those antennas will be coiled up inside that little wireframe box there with a bit of a wire going over top. Once the satellite is deployed from the rocket and safely in orbit, the wire heats up, it burns off, and the whip antennas just spring out, and then we're good to go. Okay, so the power subsystem, the last of our subsystems here, consists of 4 large solar panels covering the long sides of the satellite, and an electrical power system, or EPS, that actually provides all the power out to the other subsystems. A lot of the work this year for the power team actually went into budgeting because we don't have a lot of power generation, we do not have a lot of power, and we have a lot of things that really, really want power. So for them, a lot of the work was developing a regime where we could figure out what needs to be active when, and if we need to turn off the camera, if we need to turn off the thermal system, and exactly how we can keep our power in the green. So one of our major goals for this year that I'm very happy to say we've accomplished has been what we call flat sat testing. And that's basically just taking all the components of the satellite, spreading them out on a table, wiring them together, and seeing if they play nice together. After some initial hiccups, and it does just look like a complete mess. It looks worse in person. I believe some people got shocked working on it. So like I was saying, despite some initial hiccups, it actually went very well. We were able to test a lot of our hardware and a lot of our software. You might be able to note that there's a lot of Arduinos on this thing. That's because we used a lot of emulators. Subsystems like Payload, ADCS, and the EPS data, those are either in testing, in construction, or still in procurement. So in order to actually get the flat sat testing going, we used these emulators to pretend, basically, to hand the computer data so that it could continue to do its job and be tested that way. It also allowed us to do multiple streams of testing at once, which has really sped things up for us. Here's something I am really, really excited about. Again, I'm biased. This is my part of the project. Is that after a very long time, we managed to actually get the camera hooked up with the telescope, completely dialed in, and we've begun our testing on actually imaging stuff. These are the first images we took, just of a soldering iron held upside down. And this allowed us to empirically figure out the hyperfocal distance of the camera, which we've been using since in testing and is going to be very useful for us on orbit. And also to figure out if the camera is actually accurately giving us temperatures, because we're able to measure the temperature of the soldering iron empirically and then see what the camera is spitting out. Something else to note is that with the camera focused the way it is, this will be especially useful on orbit for determining false positives from actual forest fires, is that it can determine different parts of the soldering iron pretty well. You might note there's a little cold patch there. That's actually a hidden screw underneath the surface. Or you might notice there's a bit of a thing over here on the side. That's actually, what that is IR reflection coming off the soldering iron, bouncing off of a piece of metal nearby. So all of this has given us a lot of experience and a lot of further testing material and things to consider for when we actually have this thing on orbit. Now, this final last part, where exactly are we in our project phase? Right now, our project is currently in the procurement and build phase with several components and subsystems being readied and tested individually. And once it's completed and assembled, we will be competing in the CSDC to hopefully launch this thing. And we are very confident that we have a winning project here. Any questions?
Do you know what some of the other universities are doing, or are you keeping your work secret from each other?
Oh, there's a fair amount of communication between the teams. I know some are working on a selfie sat. The way the CSDC works is every now and then, every few years, they will change their contract, basically. So we're actually working on an older one. However, we've sent in proposals for how ours can still fit their new mission proposal, which is the selfie sat. I don't know which schools have switched over, but I know a fair amount are doing the idea is that you can use a ham radio to talk to a ground station somewhere, organize a time where the satellite can come over and take a picture of your house, and then send it to you. The only problem is it's using a camera like ours where every pixel is 300 by 300 meters, so your house isn't going to show up, probably. Don't tell CSDC I said that. I've got a lot riding on this. Our mission, our expected mission duration is not very long for the technology demonstrator, up to 5 years, I believe. However, time spent on orbit, we are making sure that it fits the requirements, that it falls down. I believe, off the top of my head, it is 25 years maximum before it comes down. We don't want to be putting any space debris up there with how littered that place is already. We don't have any kind of drag system on ours. We have been working a lot with U of T, which they had a very interesting satellite a few years back that actually had they deployed a solar drag sail off of the back of theirs, that the solar drag would just drag the thing down slowly and cause it to re-enter much quicker. We presently don't have anything like that. However, our project is still in development. We are looking at different methods of bringing it down in case we lose control early.
How are you going to test the position? How the magnet markers or whatever they are?
We're working. I'm not a fully qualified member of that team. However, my understanding of it is that we're working off of empirical data, as well as we actually have software in our lab. One of our professors works extensively in spacecraft attitude dynamics and control, so he's been lending us a lot of his stuff for actually testing how the satellite is moving around and knowing exactly where it is at what time.
Okay. We'll take 2 more questions.
Okay.
You mentioned that you've done software that you've done simulations
Yep.
on structure. Once you've got a build, do you have access to a shape and bake facility?
We do actually. We have a limited one at Carleton. We have a vibration table there, plenty of ovens around campus. What we have actually used this year, unfortunately, it didn't pan out. But in previous years, they have actually managed to get down to the DFL, the David Florida Laboratory out by Canada, and using their hardware. That's how we found out that the last structure didn't hold up.
How many satellites like the one that you're working on right now will they be launching at one time, and how will they be injecting them into orbit? Because you only have attitude control, you don't have gas propulsion, so you're going to have to establish the orbit.
Yeah. As far as I know, they're only planning on launching one CubeSat at a time. The P-pod, the carrying case of the satellite, would be bolted onto a bigger launch. I know they've done a few of them off of Indian satellites, where they'll have the big satellite on top, and then they'll have maybe 20 CubeSats from all around the world bolted around the bottom. Our mission requirement for the orbit is fairly liberal, anywhere between 400 and 800 kilometers, and we are able to update the software based on our orbit as it either degrades, or if the Indian rocket wants to throw us up at 800 kilometers instead of 400. So basically the answer is that we don't know. However, we have planned to adapt to that.
When the satellite's flying overhead, what are the limits of range that it can detect?
Our image resolution is at the baseline altitude. Every image is roughly 100 by 150 by 150K. So, however, as we're taking images, we're aiming for 50% overlap, so we're always hitting the same area twice with an image. Our resolution of the ground is, again, 300 by 300 meters, which isn't ideal because every forest fire starts off small. It starts off within that small 300 by 300 square. So that kind of limits what we can catch. However, we aimed for the kind of critical mass size of a forest fire, where once we detect it quickly, we can hopefully catch it before it gets too big to stop. I don't know if that really answered the question there. I kind of started rambling. Oh, okay. Sorry, I thought you meant individual like swath width of the picture. The orbits we're looking at right now are mainly designed to cover Canada. We're looking at polar orbits, just going over the top, dawn-dusk orbits. Every one that we have looked at has their pros and cons. However, they all cover our target area, which is the boreal forests of Canada, where it would cover the entire area roughly every 3 days, I believe.
Okay, great.
Thank you.
Thank you, Quinn. Hopefully you can field a couple more questions during the break if anyone has any. And thank you very much for your talk. That was a fascinating talk.
No problem.
Best of luck with the rest of your project. And I'll leave you with some modified words of wisdom I once heard from Smokey the Bear. Only you can detect forest fires. All right, and with that, I'm going to ask Rick Wagner to come up. Rick?
Hi, this is just a reminder. We have tickets. We're doing a fundraiser in Kingston for a pair of 20 by 80 binoculars with a tripod, Star Atlas, Planisphere, a couple of other items.
You've got all your slides of those.
Oh, okay. Okay, so Night Watch, the Pocket Sky Atlas, the one that doesn't fit in your pocket. Binocular highlights from Sky and Telescope, the Planisphere, 20 by 80 binoculars. The mouse is just for scale, so those are good size Celestron binoculars. And then a big tripod to put them all on. Total package value is about $600. Tickets are $2 a piece, 3 for $5. And it looks like I'll be selling them, I hope, after the meeting. Unfortunately, I left the tickets in the car and my wife has gone off. So she's supposed to come back and get me after the meeting. So we'll see, maybe next month. Sorry.
All right. Thank you, Rick. Yes, okay, so on the table at the side here, we've got the photograph from the 2017 RASC General Assembly, which we hosted here in Ottawa. What we're asking is for people to go to the photograph and help us identify everyone in the photo. We've identified some of the people there. We'd like to get everyone labeled, so if you could have a look at the picture. If you recognize someone who's not named, that'd be great. All right, time for the break. We are back. So I just want to thank the museum staff for getting a sort of stopgap here for our sound system. There was a bit of a citywide, or at least area-wide brownout we had there when you guys saw that flicker of light. So it's kind of reset the sound system in the booth, and they're trying to figure out how to get it going. But we've got a speaker system set up now, and hopefully you'll be able to we'll be able to enjoy the presentations. All right, so I'm going to call up Janet Tulloch here to give us her second part of her talk, Outstanding Standing Stones. Janet?
Thank you. Can everybody hear me okay? Excellent. Okay, good evening, everyone. If you weren't here for part one, I'm just going to do a quick review, so that will be a reminder for those who were and bring those who weren't here up to speed. So a couple of important points that I mentioned last time were parts of the heart of Neolithic Orkney complex, which I'm talking about tonight, on mainland Orkney. I want to clarify one thing. When I talk about mainland Orkney, the mainland actually refers to an island. But because the Orkneys are made up of something like 70 small islands, they refer to the biggest island as the mainland. Okay, so don't confuse mainland Orkney with mainland Scotland. Mainland just means the biggest island in the Orkneys. Okay. And mainland Orkney is the part of the Neolithic center or heart of Neolithic Orkney that was designated as a special site in 1999 by UNESCO. And the time period, again, that I'm talking about is sometime around what's called the late Neolithic, which is 3100 BCE or BC. I tend to use before the Common Era, to roughly about 2500 BCE. Again, there were questions about who built these stones, and more or less, archaeologists today think that it was local people from around the various Orkney Islands, and that the stones were actually quarried somewhere not too far from where they were located. There's also little doubt today that those who are studying these ancient monuments, that there's a strong cultural connection amongst standing stones, the nearby burial mounds, and the settlements throughout Neolithic Orkney. In other words, this connection encompasses ancestor veneration at a minimum, but it also seems to include communal feasting, rituals, as we'll see when I'm talking tonight, and all of it connected to the night sky. In addition, the heart of Neolithic Orkney, includes, at the very minimum, a burial mound solstice alignment, and in some cases, standing stone alignment with the winter solstice setting sun. But there seems to be far more that is going on, and we'll talk about that tonight as well. Okay, so just to remind you, the geographical area that I'm speaking about is the Orkney Islands, north of the mainland of Scotland, and here is mainland Orkney, where most of these Neolithic monuments are, standing stones, settlements, single stones, but in particular, I am interested in this small island, the most remote of the Orkneys, North Ronaldsay, which is where my ancestors are from. And this is the heart of the blow-up of this area in here, where there is just so many human anomalies going on in the landscape from the time period that I first talked about, roughly 3100 BCE to 2500 BCE. And so what we're asking is, what are the connections between the standing stones, the burial mounds, the rings, the settlements, and the night sky? And of course, there's no ancient texts that have survived from this time period that might be able to help us answer some of these questions. So we really do have to rely on astronomers, physicists, and archaeologists who are working on this material. And in between my last presentation and this presentation tonight, excuse me, I did contact the University of the Highlands and Islands, which has the Archaeological Institute, where most of the archaeologists in this, who are working in this area are part of their faculty. And I sent them a query about the standing stone in the Orkney Islands in North Ronaldsay, and I had I think the whole entire faculty responded to it. So there's a keen interest. And in fact, they said to me, if I know anything about these standing stones, could I please send them more information? One of the responders was Nick Card, who is actually the director of the Nessa Brodgar archaeological dig. So it was clearly the kinds of questions that I'm asking are similar to the ones that they're asking. So, since my last presentation, I've done further research on North Ronaldsay and the heart of Neolithic Orkney. And I am now asking myself the question whether isolated places like North Ronaldsay were in some way a miniature or modified version of the stone burial mound settlement night sky complex that we see at the Ness of Brodgar. And I'm going to suggest to you that, in fact, it is some type of microcosm, and we'll talk about that towards the end of the presentation. You recall that I talked about Maze Howe. Maze Howe is part of 13 smaller burial mounds in the Nessa Brodgar area. It is one of the oldest and largest of the communal burial sites, dating from about the period of 3500 BCE. I spoke about this site last time because it is so well known and observed for a connection with the setting sun of the winter solstice, where we have records and observations of the winter solstice sunset shining through the main entranceway of the burial tomb. So this is Maze Howe. However, in further research I've been doing and speaking with the archaeologists from the University of Highlands and Islands, Maze Howe is not the only Neolithic tomb in Orkney to experience a solstice event. It's only the most famous. Other Neolithic tombs include this one called Tavershoe Tuek on the island of Rousay. Rousay is just north of mainland Orkney, and it's one of 16 known communal burial sites where just north of Maze Howe. But this particular monument is very interesting because it has two separate chambers, one above, this one here, no, this is the one that's above, and this one is the one that is below. So in other words, it's a double-decker burial mound, which is highly, highly unusual. There's only one other like it in the Orkneys. And, but what's interesting is that both of these chambers, the upper and the lower, both have long passageways, very much like Maze Howe, and the solstice comes in on the lower passageway at wintertime as well. There's also a smaller chamber that is connected to the lower one, separate and apart. It's about 30 feet in diameter. And this main one is built on a hill so that each passageway is at ground level. One on the upside hill facing north and one on the downside facing south. The way that one archaeologist from the University of Highlands and Islands described Neolithic tombs experiencing solstice events I found was rather interesting, in that she said these tombs channel the solstice light, attributing an anthropomorphic identity and function to the tomb. And indeed, more and more of the research that I've been reading seems to suggest that in terms of speaking about the ancient ancestors, the ancestor seems to refer more to the building itself rather than the individuals inside it. And there's certainly contemporary day precedents for that when you think about the longhouses of Native people on the west coast of BC. Their longhouses are seen as a living entity, and more scholars are beginning to think that this was probably the way that the ancient Neolithic Orcadians saw it as well. So, according to one of the really interesting sites about the Orkney Islands called Orkney Jar, it's a website, it's a .com, but it's actually a very reliable website. It has been shown that the center axis of the inner passage of Maze Howe is directly aligned with the center of the barn house standing stone. This guy over here. Sorry, I've lost my way here. It's aligned with this particular standing stone, and from here the line of light travels out to strike Hoy's Ward Hill, which is an island just south, at a place where the sun sets 22 days before and after the midwinter solstice. And I spoke about this before, this idea that the midwinter solstice setting sun is not the only point of reference in this area. In fact, there is about 22 days before, 22 days after, and same with the standing stone on the island of North Ronaldsay. So in other words, there is a large temporal period where the sun is being channeled or tracked by these either the Maze Howe site and the Barnhouse stone, or for example the standing stone in North Ronaldsay. Now, by way of a sidebar, this 3-week period was referred to by a scholar by the name of Dr. Alexander Thom, who was a Scottish engineer and chair of the Engineering Science Department at Oxford University from 1945 to 1961 as a megalithic month, or a 16th of a year. He got very focused on a whole different understanding of how time was being measured. And although Thom's megalithic measurement system was highly controversial, and his hypothesis of the ring circles as astronomical complexes were critiqued by the archaeologists of the day, he was no crackpot druid. He simply, the guy was the chair of the Engineering Science Department at Oxford University, and as an engineer, he was the first to really be interested in bringing precision to measuring this about 500 megalithic stone circles in Great Britain. So he dragged his engineering survey equipment all around these various circles and did various precise measurements with the declination of objects of the night sky. So he was making a very important contribution to the science, what he believed to be the science behind the positioning of the ring circles. And his methodology actually today reverberates down to our own day, when archaeological science journals are no longer poo-pooing his approach or his methodology, but rather they are now questioning the astronomical function of these circles by asking which of the solar or night sky events do stone circles actually target, and by what method can we best prove this statistically. So he's to be remembered for being one of the first to try and bring a rigor to the way that archaeologists and scientists were approaching the stone circles. But let's go back to the Barnhouse monolith for a moment. This particular monolith stands over just 3 meters tall, or about 10 feet, at the midwinter solstice when the last rays of the sun are channeled through Maze House entrance. The sun's position is directly over the top of the Barnhouse stone. This is an observation that is well accepted as fact. It's been suggested that the Barnhouse stone was an outlier or route marker to the standing stones of Stennis Ring, the smallest on the Ness of Brodgar. If correct, then we have a definite link between the stone rings, the Maze Howe burial mound, which references the Neolithic ancestors, and the midwinter solstice. So let's take a look at the standing stones of Stennis. Let's see here. There, okay. Radiocarbon dating from the Stennis excavations shows that the site dates are at least from 3100 BCE, making this small monument circle one of the earliest stone circles in Britain. At a maximum height of 6 meters or 19 feet, the megaliths make the monument visible for miles around, which is very important because it means that the monoliths can be seen from a number of different angles in the landscape. The stone circle measures about 106 by 100 feet, and it is surrounded by an earthen henge or ditch, about 45 meters or 148 in diameter, and 4 meters across. The ditched enclosure had a single entrance causeway on the north side facing the Neolithic Barnhouse settlement on the shore of the Harry Loch. Just little remains of the ditch today, although traces are still visible around the actual standing stone. Okay. Located by the southeastern shore of the Loch of Stennis, only 4 of the ring stones now remain. These standing stones were originally laid out in an ellipsis, as determined by the remaining socket holes. Although it is thought the monument was once made up of 12 megaliths, excavations in the 1970s suggest that the ring was never finished with at least 1, possibly 2 of the 12 stones never erected. At the center of the ring, here and here, is a stone hearth constructed from 4 large stone slabs. In 1907, a flat stone here beside the hearth was lifted onto the middle stones to make the hearth look like a sacrificial altar. In 1972, it was taken down again. Excavations around the hearth in the 1970s were inconclusive, confirming only some form of stone structure had existed there, but it was not possible to accurately reconstruct its shape. In an article published in August 2016 in Astronomy Now, and a few months later in the Academic Journal of Archaeological Science, reports for October 2016, researchers from the University of Adelaide claimed their new method of statistical testing could enable the quantitative determination of astronomical connections of stone circles, meaning that researchers could now determine statistically with high confidence whether a stone circle had purposely been created with sky events in mind. The standing stones of Stennis was one of the sites examined in this study, along with the Callanish stones, which is near the village of Callanish on the west coast of Lewis in the Western Isles of Scotland. So not in Orkney, but off of the mainland of Scotland to the west. Both these rings are thought to predate Stonehenge by about 500 years. To determine whether the Stannis circle had purposely been created with sky events in mind, the researchers, using ordnance surveys, calculated declinations for the following set of targets. The lunar standstill extreme, rising and setting targets, and this included major and minor paths, and 4 extreme solstitial targets. And they did this for a number of stone circles in Great Britain. They were particularly interested in what most scholars consider to be the 2 oldest, the Callanish and the standing stones of Stannis. And for their purposes, they were interested in seeing how these matched up with later Bronze Age circles in terms of the kinds of targets that the stone circles were actually aligned with. And they found that with the standing stones of Stannis, they said that the builders engineered very particular horizon views. The northern cardinal point of the Stannis landscape is closely marked with a horizon notch, with the rising and setting of the major standstill moon placed very close to 25 degrees either side of this particular point. The diagram that I have here is not of the standing stones of Stannis. It's set up to show you the targets that they measured for each of the stone circles. So unlike other researchers in the past who were looking for particular stars that were aligned with the circle, with the stones, what they were looking at was very precisely either the sun's winter and summer solstice paths, rising and setting, and same with the moon's extreme positions, the standstill moon. They also noted landscape patterns where the rings of various circles were situated, concluding that at 50% of the sites, the northern horizon is relatively higher and closer than the southern, and the summer solstice sun rises out of the highest peak in the north. At the other 50% of sites, the southern horizon is higher and closer than the northern, with the winter solstice rising out of the highest horizons. The stones of Stannis site fits into the latter grouping. And according to their calculations, the likelihood of the monuments of the standing stones of Stannis built purposely for astronomical reasons is above 97.87% for Stannis and 97.87% for Callanish. If you're interested in how they made these measurements, I have the information on the article and can give it to you afterwards. Of interest, the function of the Stannis ring was connected to the moon through Scottish folklore, with one of the earliest accounts written by a Reverend James Wallace in 1684. And he states, several of the inhabitants of the area have a tradition that the sun was worshipped in the larger and the moon in the lesser circle. So folklore seems to coincide with what some of the academic research suggests. The Ring of Brogar, which is all part of the Ness complex on mainland Orkney, is thought to be part of a geographical area that includes the stones of Stannis, which is approximately 1 mile to the southeast, and probably something called the Ring of Buchan to the northwest, and the actual Ness of Brodgar, which I'll talk about in a minute. Unfortunately, for the Ring of Brodgar, there has been limited scientific investigation of this site. Some work was done in the 1970s and again in 2008. Archaeologists estimate the building of this ring was begun around the year 2500 BCE. Given there's never been a major excavation of the entire site, dates for its construction are somewhat vague. We do know that Brodgar is significantly later than the stones of Stannis. The ring is composed of an outer ditch or henge, 340 feet across, measuring almost 10 feet deep and about 16 feet wide, the actual ditch. When the ring was erected, the Stannis loch did not exist. Instead, the area was a wet, marshy bog surrounding pools of water. In other words, the henge was likely filled with water. No one is quite sure which came first, the henge or the stone circle, but when the circle was finally finished, it resembled an island of standing stones. Opposing causeways, still visible today, give access to the ring in the southwest and northeast sections of the circle, confirming that the ditch around it was most likely filled with water. The circle of standing stones possibly numbered as many as 60 initially, but now only 27 survive and are standing. They are much lower than the circle in the standing stones of Stannis, at about 7 and 15 feet. The Ring of Brodgar is practically in the center of a massive physical landscape, which looks like a natural bowl formed by the hills of the surrounding area. From the circle, Professor Tom, our Scottish engineer, chair of engineering science at the University of Oxford, who all the archaeologists laughed at, noted that the natural features in the surrounding landscape seem to serve as distant markers for the rising and setting of the moon. A sight line to the cliffs of Helia on Hoy, for example, seemed to mark the minor southern setting of the moon, while a notch on Mid-Hill to the southeast defined the minor southern moonrise. So he was going at that time by his own calculations. But today we have scientists who are actually using his approach and ironically are being published in the Journal of Archaeological Science. According to Colin Richards of the University of Highlands and Islands, a geological examination of the Brodgar megaliths confirmed that the stones had been brought from different areas across Orkney. These quarries and the different types of stone obtained from them, in his view, represent the different communities involved in the creation of the stone circle, but nothing beyond that. In other words, they have, in his view, no ritual function. He suggests that it was the building of the circle itself that formed a kind of ritual, or even a competition amongst Neolithic communities. Now, I included this slide because using my app, Stellarium, I thought it would be really interesting to take a look at the Ring of Brodgar in December 21st, 2500 BCE at around 4:20 in the afternoon to see where the orientation of the Milky Way was. Some archaeoastronomers have suggested that the Milky Way may have played a part in the ancestor ritual. For example, in some ancient religions, ancestors had to travel to the afterlife, and so there is an interest in whether or not the Milky Way was seen as a path for traveling for ancient ancestors. And it is interesting that if I can trust the algorithm on this app that it does tend to show the Milky Way here coming down roughly in the same area of where the sun would have set on that day, if you could have seen the sun, as Orkney tends to have really bad weather. Now, other scholars suggest that the rings of this area point to the veneration of ancestors. In other words, they do have some kind of ritual function. That the fact that the rings are surrounded by, the ring of Brodgar in particular here, is surrounded by a complex of Bronze Age burial mounds, cairns, and prehistoric earthworks, that there has to be links between ancestral veneration, the mounds and settlements, and the night sky. But it's still a hypothesis that is still very difficult to prove, but it does seem that we are moving towards having methodologies that can begin to explain what the purpose of these rings were. The most visible of these burial mounds are known as Salt No, Fresh No, South No, and Plum Cake No, because it looks like a plum cake. And the No simply means that they were mounds. Over time, this site grew. Obviously, it wasn't built in a day, and undoubtedly had a number of different functions. The causeway through the island of stones certainly suggests, at the very least, a procession of some kind, so that late Neolithic and Bronze Age people entered and exited the circle, perhaps on their way to another ritual. I want to draw your attention here to the standing stone called the Watchstone, because like the monolith on the island of North Ronaldsay, it is a solitary stone. It's an outlier from the stones of Stennis, and it lies within really a few feet of the stones of Stennis and not far from the Ring of Brodgar. At one time, there was a smaller second stone beside it. Given their placement, it's likely the two megaliths were once part of a stone-flanked ceremonial route, like the one at Callanish, which I showed you earlier, between the Ring of Brodgar and the standing stones of Stennis. At the very least, this stone and its mate pointed, or at least framed, a view, and perhaps was even seen as a type of doorway between the two rings for those who were walking between them. The Ness of Brodgar, which we're looking at here, and you can see there's the standing stones of Stennis there, and the little stone I just showed you there. So you can see there, and the Ring of Brodgar would be up here somewhere on the floor. So you can see that the whole complex is physically very close to one another, and that the mound of Maze Howe is somewhere over here. The Ness of Brodgar occupies a very central position within this Orkney archipelago between the two lochs of Stennis and Harry. Stennis is salt water, Harry is fresh water, in the middle of the island's most imposing complex. From the Ness, you can see the Ring of Brodgar, the stones of Stennis, Maze Howe, the Watchstone, and the Barnhouse Stone. On the south side of the Bridge of Brodgar, barely 300 meters distant, is the Neolithic settlement of Barnhouse, which is down here. So we have Neolithic settlements very close to these rings. The difference between the the site that we're looking at right now and a settlement is quite substantial, because the site that we're looking at here, the Ness of Brodgar, wasn't just any sort of settlement. It was a massive complex of buildings. The archaeology for this particular site is still ongoing, and using all the latest kinds of scientific information, the closest dates that we have for it are around 3100 to 2900 BCE. And it appears that it was, they have found a very huge freestanding buildings that used to have tiled roofs, and all of this complex was enclosed by a massive stone wall. So something far more important than a settlement was being built here. Structure 10, which was this one over here, Structure 10 was erected in 2900 BCE, and it was the last major building to be constructed. The archaeology from the peak period suggests that people were feasting and exchanging objects from very far away at this particular site. Its last use was sometime around 2400 BCE, when approximately 400 cattle were slaughtered and deposited around the structure. And the testing for the bones of the cattle is all around the same time period, which suggests that there was one kind of final feast before this place was decommissioned as a large communal site. All of the main structures of the Ness have yielded examples of decorated stone, which now total well over 800, and range from stunning examples of deeply incised, here. Deeply incised, pecked, and cup mark decoration, and a large proportion of lightly incised markings. The site's communal buildings cluster around a very distinctive decorated standing stone. Again, another link to the stone circles. Numerous finds hint at long-distance contacts. Pitch stone from Erin, which has only been found at 2 sites in Orkney, an axe blank from the famous Neolithic axe factory at Langdale Pike in the Lake District, and amber beads representing the most northerly occurrence of these in Orkney, and most likely coming from somewhere in the Baltic area, and striking parallels with the art from the Boyne Valley in Ireland. The same researchers who analyzed the standing stones of Stannis that was published in 2016 state that, and now we're looking at the remaining standing stone on the island of North Ronaldsay, state that single standing stones are associated with or part of monuments dating from the late Neolithic to the late Bronze Age, which would put this stone in roughly the same time period as those at the Ness of Brodgar. Of the 5 responses I received from the University of Highlands and Islands archaeologists to my query about this particular stone, Julie Gibson wrote, "Standing stones are usually thought of as part of a Neolithic landscape." Yes, we know that. Some, as I have heard, alleged with the North Ronaldsay stone are passive participants in sun events. For example, the Barnhouse stone, which we looked at, Maze Howe. Others may be thought of as route markers. Each may have its own particular story to relate. Nick Card, who is the director of the Ness of Brodgar site, responded to me, sending me a number of pages to look at, which included the following information. I was particularly interested in what was said about the sandstone is referring to this standing stone, which I just showed you. And the information on this is that, which caught my eye, is right over here. There may have been a stone circle at Torness on the west side of North Ronaldsay. Torness is here. North Ronaldsay is this entire island. You'll also note that there's a site here called Howmay Bray. So Howmay Bray is an ancient settlement about the same age as Scarabray, and you may be more familiar with Scarabray, which is a Neolithic settlement on the mainland Orkney. So we have Howmay Bray, we have Torness, which may have had standing stones, and we have this standing stone here. Now, according to the archaeological record from the Historical Environment, Scotland, what has been found at Torness is a number of small rings of stones measuring 9 feet in external diameter and rising only about 6 inches above the ground, showing little depth of soil. The stones have been carefully placed, and some bear marks of the fire recalling those found in larger mounds of prehistoric date. We might dismiss this finding as insignificant if it wasn't for the 11 turf-covered stone mounds or burrows varying from 3 meters to 12 meters in diameter found in the same area. So here is the ordnance map here, which shows where all the cairns are, or the ancient burial sites in Torness, but it doesn't show anything referring to any circular potential of circular stone sites. But I remembered that my dad, who was from North Ronaldsay, had made a map of the island before he passed. And so I ran upstairs to have a look at his map, and sure enough, in the same area, I found what I think is his reference to the cairns and these little circles here. Now, he passed in 1974 and was born in 1903. So these stone circles would have been very familiar to people who were part of the island at that time period. And it looks like he was trying to remember what they were called, because he had a name here and then he rubbed it out. But it's interesting that it appears on his map, but these stones don't appear on the official Ordnance Survey maps. I trust his map. With all of this, we don't have an exact date for this little complex. All I have are the archaeologists who talk about single standing stones as being part of the same period as the larger rings. And where I am going to from here is that given that we have a Scarabray-like settlement not far from the standing stone, and we know that there are prehistoric graves and possible stone circles, small ones up here. My question is whether Neolithic North Ronaldsay, the most northernly and isolated of the Orkney Islands, was a microcosm of similar activity and Neolithic placement as what occurred on the Ness Brogar, especially at the time of the midwinter solstice. Because as I've shown you before, we know that the standing stone is aligned with the sunset of the midwinter solstice. Travel, if we think about it, if we're talking sometime around 2500 BCE, there's no wooden ships at that time. at least not on Orkney, because Orkney doesn't have any trees. So travel at that time of year in a small craft from an isolated island to meet up with other communities who may have been celebrating the midwinter solstice at the Nessa Brodgar would have been highly dangerous. I myself was stuck in North Ronaldsay in the much warmer month of June when a gale blew up and the car ferry, which is far more substantial than a small craft, could not make the crossing from the Orkney mainland. So given their own route marker stone and a similar sky to that of the mainland Orkney, I would suggest that people on North Ronaldsay could have followed the same type of stone settlement ancestor cosmology as others throughout the Orkney Islands and beyond, and could join in on the midwinter solstice festival celebrations, but from the comfort and safety of their own homes without risking the treacherous crossings to the mainland in a small craft. Thank you.
Thank you. So we've got time for maybe 2 or 3 questions, if anyone has any. Yep.
The land in Europe, and I've seen this for instance against wall, grows at about a foot a century. So why aren't these things buried?
A good portion of them are buried. The large stones at the Ring at Brogar have a substantial, it's like a tip of the iceberg situation, so that over time the top part of the stone has been erased and so on due to weather. I mean, they are called monoliths for a reason. They're large enough that even over time, it would be very difficult to bury them. They're also in incredibly windswept and rainy areas. So I would suggest that that the weather conditions when they were first built probably contributed in somewhat to their survival. It's a good question, and I know that what you're speaking of, because I've worked at archaeological digs, but they were never uncovered in the same way that the Skara Brae settlement, which was buried in sand dunes, was. But there is a substantial amount of stone underneath the main level of the circles.
I've been to Knoeth in Ireland. It's just north of Dublin, and the mounds there are very similar, and the age is similar to the ones in Orkney. Now I'm wondering, is it the same people that built them, or was the expertise kind of carried back and forth between them?
Yeah, I think it's part of the same cosmology, to be honest. I mean, I didn't talk about Ireland because I would have been here all night, but I've been looking at some of the burial mounds in Ireland, and their markings are very, very similar to some of the finds I showed you from the Nessa Brodgar. So I would suggest that it's a similar cosmological system, but it doesn't necessarily mean that the same people built it. It does suggest that there's a large geographical area of people who may have believed in the same, I don't want to say religion, but same sort of beliefs that in the Northern Isles there.
Okay, one last one.
Janet, the mound you have with the twin, the upper and lower,
Yes.
could you put that up there for a second? Or is it possible?
Yeah,
I had a question about that slide.
yeah, no problem.
Find it. I don't know. Which one is it?
It's on the island of Rousey.
Yeah,
Yep.
that one there.
Mm-hmm.
The one on the upper left, it looks like the entrance is facing almost north.
That's right.
Did the summer solstice or winter solstice get in there?
It would have been summer, because the winter solstice, the winter solstice in Orkney is never directly west, right? It's south-southwest because of,
To the Arctic Circle?
it's 60 degrees, roughly 60 degrees latitude.
Okay, yeah.
Yeah,
So it's almost to the north. That's cool.
yeah. Yeah, this is the only dual cairn that they have found. There's only one other, and they have separate entranceways with the long passageway. And again, it would have been the lower one, the one that has the 19-foot passageway that had the winter solstice event.
Okay, thanks very much.
Okay, thank you.
All right, and we're going to jump right into observation reports. We are running a little short on time, so I'm going to ask folks to keep it brief if they can. So first up, we've got Doug. There you are. So before you present yours, I do have a plaque to award you for best presentation of the year. You have also been conveniently absent since winning, so thank you very much, and congratulations.
Thank you very much.
All right, and I'll let you take it away. Just click one to the right there.
That one, okay. Hi there. Just a little late presentation about the eclipse. I was in Ottawa looking from my balcony, and it was definitely cloud covered, but you'll see the results dashing out every once in a while in the cold weather. It was still possible to see something.
I think you may need to click it one more time there.
Be very careful. There's a lot of ice on the balcony, so that any slightest nudge of the tripod. That's very much what it looked like just with the eyes. Not much more impressive with binoculars. Saturation back to normal, or just back to normal here is actually even better than what was predicted. That's it.
All right. I think, Jim, you're up next. Just click.
All right, I tried to go for the lunar challenge for last month, which was Bailey Crater, and it's an excellent opportunity to talk about libration. Libration is not the drinking of beer that many of us will be doing later. It's something entirely different. It has to do with the fact that, from our perspective, the moon sort of does a little hula dance. And I brought a optical aid here. And here's my moon. So there's a couple of things that are combining to allow us to see more than just the half of the moon that's facing us. We can see about 59%. If the moon is rising or setting, we can kind of see a little bit around each side. Also, depending on where it is in its orbit, because its orbit is inclined to our Earth's orbital plane. Sometimes it's a little bit above our orbital plane, sometimes a little bit below. So we can see a little bit on the top and the bottom. So that's kind of the most easy to understand reason, but also on top of that, the moon has kind of an irregular orbit, much like the Earth's. It's an ellipse. And depending on where in this elliptical orbit it is, the moon's rotation can be a little bit ahead or a little bit behind because its orbital speed is changing in this elliptical shape, but its rotational speed is the same. So it kind of does a little as it's going around. And then on top of that, its rotational axis is tilted, just like the Earth's. It's about 6 degrees off of its orbital plane. So as it's spinning, we see sometimes a little bit more to this side, a little bit more to this side, sometimes a bit more to the top, sometimes a bit more on the bottom. So all that combines into what's called libration, and it's kind of like a little hula dance that happens over the course of the year. And to give you an idea of the extent of what libration can do, this is a picture I took back in 2015 that clearly shows Bailey crater here at the bottom. The whole crater is visible, and you can actually see the craters in behind it, which are technically past the what you should be able to see. It's past like the 90 degrees of longitude. Now, 9 months later, you can't see Bailey at all. It should be right here, but you can't see it because the moon has tilted the North Pole towards us, and we can no longer see it from our perspective. Now, I wanted to see what it looked like using this is quite a while ago, so my imaging techniques have advanced a fair amount. So I wanted to try again. About 3 weeks ago, I tried just to see what we can see of Bailey. And this is what it looked like. So a favorable libration just by chance. I didn't look it up or anything. I was just lucky to catch a good view of Bailey. So this looks elliptical, like Schiller up here, but actually it's a perfectly round crater. If you were to look at it from underneath, it's round. It's about 300 kilometers across. It's quite an old crater, very beaten down. And some think that the structure here is actually a ring, so that it's more of a basin than a crater. So this is, I don't know if you know, if impact craters get large enough, the central peak becomes more of a ring shape. So yeah, there's Crater Bailey. Thank you very much.
All right. Up next, we've got Richard Taylor. The right one advances, yep.
Okay, like many of you, I've been getting a bit tired of Ottawa's winter, the cold, the snow, and the lack of clear nights. So I was fortunate enough to schedule a holiday down in Belize. I just got back on Monday evening. Now, one of the things I've been trying to do from Ottawa is get some better pictures of Orion, but with Orion higher in the sky and much, much darker skies, I finally managed to catch the Flame Nebula. I think if I squint hard enough, I can maybe make out the Horsehead somewhere down below there as well, somewhere in there. I still have a lot more processing to do, but I think I can bring this out a little bit better. There's something we don't see from Ottawa, Omega Centauri, a beautiful globular cluster, and that was quite easy to get pictures of too. And the seeing was not so great, but I really lucked out. We were on a little tiny island off the coast of Belize, and I had 5 straight nights of clear skies. So I followed my sky and telescope map for Pallas and managed to spot it moving from there to there, to there, to there. Sorry, and that's a selfie of me. I've been trying to get pictures of Pallas from Ottawa again. I did get one just the other night, but the exposures that I was using in Belize completely washed out the image here in Ottawa with the sky glow. So there's some stars you never see from Ottawa. And the southern Milky Way, and I believe I got, yes, the Southern Cross down here. So this is mostly Carina, Argo Navis, the big constellation, but I can't tell you much about the constellations. It was just a beautiful, beautiful stargazing experience. Highly recommended. Thank you.
All right, thanks very much, Richard. We've got Rick Wagner up next.
Well, good evening. So first, that's mislabeled. This is the challenge object for last month, I think. So this is actually a planetary nebula. And what you can see, this is shot with the 40 centimeter Boltwood scope with a diffraction grating instead of a filter inside the camera. So what we get is what's called the zero order image. So this is the actual planetary nebula. You can see its central star and the little disk around it. But then it also produces a spectrum. And so you can see that for each spectral line in the light that's emitted by the nebula, there's a little picture of the nebula spread all along here. And then, of course, the central star has a continuous spectrum, so it runs through the middle. So you get, with this one, you get both the straight-up picture and the spectrum. I've been trying to figure out what the wavelengths of these lines are. I haven't managed to do that yet. So then I'm on the science team for the RASC's remote telescope. What we're trying to do is get some of the scientific background for the scope, signal-to-noise ratio for various filters and exposures, transformation coefficients, the astrometric constants and stuff. And so what I've been doing is shooting some asteroids lately. Now, I don't know, is this a video?
I don't remember.
And can I make it go?
It is a video. If you click, it'll go.
Okay. All right. So what we have to do is you have to go to the Minor Planet Center and get an observer's code. Basically, you get yourself certified as a competent observer. So you can see, you take pictures of 2 or 3 asteroids several times on a given night, separated by about a half an hour, and then you do the same thing again a couple of nights later. You measure them all up, you provide them all kinds of additional information, and then they say, yes, the observations are good enough. So you can see this is 3 of the sets. This little asteroid here, it's about 16th magnitude, I think 941 Murray. And so you can see I took a couple of pictures, and then a half an hour later, 2 more, and then a half an hour later, 2 more, and then I did that again a few days later. And I've submitted it all, and I haven't heard anything back from them. So I'm still wondering, have I got a mistake in the format or whatever? But anyway, while I was getting interested in asteroids, I thought, I'm also the president of the Kingston Center, and so some of the interested members down there, for instance, Terry Dickinson, 5272 Dickinson is named after him. So one of the members down there thought it would be neat if we took pictures. So there's Dickinson. You can see bobbing around in the field of view. Now, I took these and then was processing them in the car on the way to Kingston, so I hadn't actually looked at them when I displayed them. But you can see everybody else pointed out, hey, Rick, you've got another one there. So I had to go back home, and then there's actually a service with the Minor Planet Center. You can go and say, I saw an asteroid at this location at this time. Do you know about it? And they will come back and tell you which number it was. and I don't remember offhand what number this was, but it's somewhere up around 320,000 is its identifying number. So the next one I imaged was 6115 Martin Duncan. He's a professor emeritus at Queen's. This one's a lot fainter, and oh, no, there it is. So it's down about 18.5 magnitude. And of course, everybody else said, "Oh, Rick, you got another one." So, okay, so that's 2 extra ones. And then it turns out that this one is really a lot fainter than I thought it should be. And it's actually, and it's actually displaced a little, about an arc minute or so from where it should have been. And so I did some more investigation and discovered that's not actually the right asteroid. The software I was using was giving me a wrong prediction for Martin Duncan that was almost on top of another asteroid. So that's 3 asteroids in this set of images that I've stumbled across. And this is actually Martin Duncan, and also an airplane, and an extremely bright moonlit night. So I did eventually find the proper asteroid. But this got me interested in the idea that if I'm seeing so many asteroids, maybe some of my deep sky images, I'm also getting asteroids. So here's an image I took of a dwarf galaxy, UGCA 205, also known as Sextans A. It's about 5,000 light years across, about 4.3 million light years away, so it's sort of on the outer limits of our local group. And you can see I also caught a satellite track through here. But sure enough, if I zoom in, and you can see there's an asteroid, or something anyway. So I submitted this to the Minor Planet Center, and they said this thing is about 21st magnitude, and they say there were no known asteroids brighter than 24th magnitude at that position. So I've submitted the observation as a discovery. Unfortunately, I only observed it on the one night, and so until somebody else stumbles across it and they get an orbit, hopefully they will produce the orbit back, connect it to my observation, and I will get credit for the discovery. So just to help you see it even a little better, I can stack all the images together on the asteroid, and it is a nice little point. You can see all the stars are blurred out with motion. So somebody told me that 6478 Gault was an interesting asteroid. It was discovered in 1988 by Carolyn and Eugene Shoemaker. They were comet hunters and asteroid hunters and stuff. And so you can see, oops, well, I kind of spoiled the effect there. And I can't go back. There we go. So that's the thing there. And it's about to suffer what I call a YICF, a Yorp-induced catastrophic integrity failure. Al mentioned earlier the Yorp effect. The sunlight on an object like this can cause a torque on the object, and it starts to spin faster and faster. And if it's a pile of rubble, eventually it will get to the point where it starts to actually fling itself to pieces. And what that causes, if it goes again, there we go, is it turns it essentially into a comet. So you can see it has 2 tails. And I mean, that to me is just a spectacular tail. It's so narrow, so long, so straight. And then, so presumably this is a gas tail and this is the dust tail. So I've been imaging it. Nobody has determined the actual rotation period of the asteroid, so I've been imaging it for a few hours every night since to try and get its rotation period. And of course, also watching to see if it actually starts to break up into individual pieces. Thanks.
All right. Thank you, Rick. We've got Jim Sophia up next. That one advances, and it's a laser pointer at the top.
Okay. So despite the light pollution of Ottawa and the cold weather, I still had an opportunity on a few occasions to image some deep sky objects from my balcony using a good light pollution filter. And I had my 8-inch Celestron SCT with the Malincam, and I ran wires into into the living room where I had my PC, and it was nice and warm. And so, and I was able to control the scope using Stellarium software. So these are low resolution images, but nevertheless, they're fairly decent for the fact that we had some light pollution and so on. So this is M1, and it's a 22-second exposure using ultra high contrast filter.
Jim, can you face towards the mic so that we can
Yeah.
hear your voice?
Oh, and I could see it right there. Well, here we go. All right, so that's M1, supernova remnant in Taurus. And this is M3, a 12-second exposure using a light pollution filter. And here is a 3-second exposure of our favorite, M42. And this is a close-up of M42, a 23-second exposure. And this is the Horsehead Nebula using an H-alpha filter, 21-second exposure. And last but not least, this is the Flame Nebula using an H-alpha filter, 23-second exposure. So it's really a lot of fun. Thank you very much.
All right, thank you very much, Jim. Next, we've got Damien Robertson.
Can you remind me again?
Advance the slide and laser pointer.
Laser point, perfect. Okay, thank you. Hello. First, I will give a little bit of apology. I'm coming off the tail end of a cold, and my voice hasn't recovered yet. But I had a pretty tough winter, but I managed to get out on Saturday, March 23rd, and the goal was to take a wide field shot of the center of Orion, so the Orion molecular complex. So just to sort of place you here, you've got the 3 belt stars of Orion, and then M42, or the Sword of Orion, and then this is just the northern edge of Barnard's Loop, along with M78. And this is a total cheat because I have 2 challenge objects from 2 different months in one shot. So, so I took this image from the FLO, and it was actually my first time at the FLO, and I think it's become my new favorite place. The warm room, the washroom facilities, it was all really great. It was a little bit spooky. Another member showed up, so I was very grateful for that. I had a owl fly over my head at one point. Right, so this part of the sky holds some sentimental value for me. Back in grad school, I used to give some planetarium shows where I would talk about star formation. And I would always use NASA images instead of any of my own, so I'm very happy to have one of my own now. And so I guess just to give you a size here, so we're about 9 degrees across. This was taken using a 135 millimeter lens, stopped down to f2.8. And this is a stack of 58 sub-exposures, and each sub-exposure was 45 seconds long. I had to dither every few sub-exposures manually, as I was just using a very small portable mount that tracked the night sky, so there's no guiding or anything. And so this is at half res. I've got some full resolution crops here. So that is M42. And and the Running Man Nebula, and then this triangular little shape down here I looked up is NGC 1999. All of this diffuse dark brown, that's like dust, which is just what astronomers call like micron-sized silicate and carbon. What I usually really like about M42 is, and everything that you're actually looking at this picture is about 1,200 light years away, so it's very close to Earth. It's a beautiful example of star formation, but stars form together. They form in a litter, and then every so often you'll get a very bright, powerful star form, an O or a B star, and they're powerful enough to put out huge amounts of stellar wind, and they halt star formation in sort of the local area. And if that happens to be near the edge of a molecular cloud, it blows a cavity in the side of it. So when you look at M42, you're actually looking into the cavern and seeing like the star formation on the inside. So this is the orientation that maybe you're more used to. So the three belt stars of Orion, I'm going to butcher these names, but this is Alnitak, Alnilam, and Mintaka. The Horsehead Nebula with all the H Alpha mission, the Flame Nebula, and I was able to pick out NGC 1990, which is this faint reflection nebula, and these two bright globules, these reflection globules, which is IC 426 and IC 423. And then this is M78, which is the challenge object, I think, for March. And then the northern edge of Barnard's Loop, NGC 2112, which is an open cluster. There's a ton of extinction here. It's very dark, and that's the dust basically obstructing all the light from, I guess, behind it. And I think, oh, okay, yeah. So this, so previous to the picture I just showed you, the last success I had was way back in January, before we just got crushed by winter. And I was testing a monochromatic camera in my backyard. And I just aimed it at the Pleiades, so M45. I took about 20 minutes worth of exposures before the computer sort of froze up. And when I stacked the images, it turned out to be something quite nice. So, yeah. Cool.
Thanks very much, Damien. All right, up next we've got Bob Olson. Bob Olson. There you are. That's right.
The other right hand. This way?
Yeah, you're hitting the right button, but maybe Chris has to advance it for you. Okay, now hit it. There you go.
There we go. Yeah, this is M46, in case you can't read. All right, Chris, you want to go back one? There we go. M46 again. M46 is a star cluster, open star cluster, about 500 stars, and that's not what the picture is. This picture is the little planetary nebula in the middle there, and I found that probably 10 years ago by accident, and I was astonished, but I never had a really good picture of it. So I decided to aim my camera at it this time and take a slightly better picture. And I think the planetary, the cluster's 4,000 or 5,000 light years away, but that planetary is only 3,000 light years away. So it's on this side. It's not actually part of the cluster at all. But it's has a kind of a M57 look to it. This cluster, by the way, M46, is just a little bit west, a little bit east, I guess, of the Orion Nebula. So it's not visible very easily right now. I took this in just before I left for Orlando for the winter. I had a tough winter there too. It was a lot of light pollution. This is a slightly different picture of M51 that I'm used to. I took all the focal reducers and everything off of my telescope, and so this is being taken at f11 at about 2,700 millimeter focal length. And so it's a nightmare to focus it. It's also a nightmare to find anything with it because it's like looking through a straw. And
So focusing and guiding were all a problem. Getting it all aligned were a problem. And Eric LeMay actually came over one night and wasted a good part of an evening showing me how to do it. So I really owe him a vote of thanks for it. But it's got a lot of detail that I never was able to get before at the shorter folk lengths. By the way, M51 is a perfect object of view right now. You can take pictures of it all night if you want. It's basically up all night. If you sort of think of the Big Dipper as a sort of like a dipper, it's like where your knuckles are on the handle, just a little bit below the handle. So it's easy to find, easy to see. It's I think it was the first galaxy that we ever saw a spiral structure in. And the Owl Nebula. If you took the Big Dipper and pretended it was a fly swatter and smacked a spider, where you hit the spider with would be about this M97. It's a planetary nebula, and it's quite a ways away, but it's really big. It's about 1 light year across. And as you can see, it's at 2,700 millimeters, it looks pretty big. Thank you very much.
Okay, up next we've got Taras. So we are running a little bit over time, just for the rest of the guys that are coming up next. If you guys could just keep it brief, please, before the museum chases us out of here.
So every year there is a winter star party held in Florida, and this year I attended it with Konstantin. We took some pictures there, and we traveled 2,900 kilometers from Ottawa to Key South. And so the size of the island where the party is held is actually smaller than resolution of the screen. So it's like would be less than 1 pixel size. And it's good because it's so small, and the distance from this island here and this island here, it's quite dark there. However, the proximity of these islands gives you big light domes on both sides, on east and on the west. So it's not really perfectly dark, but pretty decent. So as you know, the Keys, it's a sequence of these islands here connected with a bridge, and you go about an hour, perhaps, for this little thing here called Camp Visamki, which is the southern part of this island. It's actually 2 campsites here. This one here is the Girl Scout camp, and this is Boy Scout camp. So what happened is a year and a half ago, Hurricane Irma swept through the Keys and destroyed lots of things on this island, including this house here, which used to be a facility with showers and washrooms. So this year it was not operational. Instead, we were using this one here. And it did the damage to the trees along the shoreline. So last year, actually, this winter party was not held at this place. This is the first time that they reopened after the hurricane hit the place. And you could see that there were still lots of things not perfect, including lack of electricity on the island, at least on this portion here. If you want to go there, so from the entrance, if you're with RV, this year this portion was dedicated to the RV campers, and this was for the tent campers. And so we left around like first days of February, Ottawa, with cars skidding on the roads, with lots of snow, with quite cold temperature. And as we moved gradually to the south, we saw how the picture is changing. It's getting kind of milder, and then more pleasant, and then even more milder, and then hot. We had to turn the air conditioner on. And then Florida, it was quite different story, but it was a good feeling. It's like we belong here in the middle of the winter. So when you reach the highway, it's quite picturesque sight. You can see the colors of summer with beautiful water, and the skies are very clear. It was pleasant indeed. We camped, so the campsite itself is pretty close to the shore. So, think I clicked back button. Oh, there you go. So these are the trees that I mentioned that were damaged by the hurricane, and they still didn't revive. The palms grow under, I don't know, 70-degree, 60-degree angle. So it's not really perfect condition, but and to give you an example or a feeling about the size of the party, I think this year there are at least 370 participants, judging by the number of tickets claimed at the door prices. And yeah, so this is what it looked like. There were different people with different equipment from all of the North America, with the telescopes, self-made, commercially sold, just with binoculars, and enjoying the dark skies in the middle of the winter, which again was really something which was needed in the middle of cold season. Some people during the day had their telescope up, like this gentleman here was showing the prominences on the sun, which was quite amazing to see during the day, and you could see them evolve and move within the span of minutes. And again, this is the tree line which would separate the two parts of the island, and behind this tree line there's this Boy Scout camp. So we camped somewhere here in the corner, somewhere right there. If you go to the shore and look to the east, you would see a little bit of the, again, the breeze from the hurricane. It's still there. This is a bit better picture. That long bridge, people doing the observations and astrophotography, especially those who needed to have a clear horizon to the south, set up right on the shore as well as we did. And to the west, you could see the Keys West, and there was actually light pollution in both cases, pretty bright from this side and this side where the marathon is coming, and kind of was a little bit of a spoiler, but direction north was really dark. And again, the sunset, because skies are so clear and the best quality of the sky is seeing, I think it's the main reason why people go that far, is because not only you enjoy the dark skies and mild temperature, but the seeing is quite amazing. So this is picture of the moon with the earth shine in it, and when you look closer, you would see the earth shine quite nicely, or changing the exposure, you'd see some details. This is still with the moon pretty low, so the seeing, even in Florida, when the objects are so low, seeing is not perfect. But as they get higher, the story changes. So I showed this picture last meeting, but I just want to show this unusual effect, which is diffraction rings around the stars, because you can only see them where the seeing conditions are pretty good. And this is the core of the Orion Nebula with the star formation regions. This is planetary, protoplanetary disk with tiny star in it, which normally you wouldn't see from these latitudes. Eskimo Nebula, it's planetary nebula. Again, only because of good seeing, I could take this picture, because it's really tiny object. When you look at it with your eye, you wouldn't see it if you look at it directly. You have to use your avert vision, and then it kind of blinks on you. All of a sudden, kind of appears. When you look at this star here, you'd see this little smiling face. But if you look directly at it, you wouldn't see it. So this was, again, just because of a chance to take a nice high-resolution image, I used that chance to show that planetary nebula. Jupiter would rise shortly before sunset. This picture was taken when it was still very low. I don't know, maybe 15 degrees on one day, and the next day the time difference is 1 hour, and you see how much of the details there is. Like this is first image and this is second, so in an hour difference the details show up much better. The planets, so right below Jupiter there was Venus, and I used the ultraviolet filter, which allows to see a bit of the cloud cover details. I added this dirty color for just to imagine what the clouds would be like, because it's not really visible in a telescope in a visible range. And Mars was pretty high early evening, right above the horizon, but it's pretty far from us now. It's size of 1.5 size of Uranus. So, however, on Mars, you can still see a little bit of the details, even despite the fact that it's so tiny. This is the non-scaled picture of the original size. Thank you.
So we traveled together with Taras, and I also, no, Taras, this is yours.
Yeah, sorry. Yeah, I forgot about this. So, yeah, Uranus, when I stretched the, oops.
No,
oh.
you screwed it up.
No, I pushed back button. I don't know.
I don't know what happened. Uh-oh. Chris is going to have to bail us out here. There it is.
So the Uranus picture, when I stretched it, apparently I was able to capture some of Uranus's satellites here, which can be mapped: Oberon, Titania, Ariel, Umbriel, kind of, and if you really stretch the imagination, there is maybe something showing up here, maybe not. But
Thanks, Taras. This is really good. So I was only using my inexpensive DSLR with a kit lens. I piggyback it on top of my SCT, which itself is mounted on Altaz mount. So my exposure times are limited to 15-20 seconds. I typically will set a higher setting of ISO and make a lot of such pictures and stack them together. So this is a stack of around 100 such frames. Well, it's never enough, of course. This is area to the east of Sirius. Oops, this is Sirius here. So, yeah, there is nice chromatic halo. This is a bright star, obviously. There's a lot of things here. Basically, there's a lot of open clusters in this figure. So I try to annotate. Hey, it's not moving. There it is. So there are 3 Messier clusters here. M41, M47 are 4.5 and 4.6 magnitude clusters. They're visible to naked eye. This is M46 that was talked about just recently. I believe you could see, I don't have a close up, but I could see that planetary nebula there. These NGC clusters, they are all 6 to 7 or 7 to 8 magnitude clusters, so actually very nice binocular targets. And you can actually spend a good hour or two just studying this area here. This is in fact what I did while this picture was taken, and was a lot of fun. Also, I was doing sketches. So this is my sketch of Orion Nebula. I actually don't do sketches too often because this is a lot of work for me. This one took a good 1.5 hours for me, and this would not be possible in Ottawa weather, obviously, but there it was quite comfortable. And my last slide, actually this is a movie. How do I get it playing?
Just click one more time.
Okay. Oh yeah. So last day it wasn't really that clear, so no good long exposure, no serious long exposure work could be done. But this is just a time lapse from the shore, and this bright star here is Canopus, which is Alpha Carinae. This is the second brightest star in the sky. After Sirius, and the third one I believe is Vega. Yeah, it's not visible from Ottawa, but it was visible from there. That's it for me.
Thank you. Right, and last but not least, Paul.
Thanks, Oscar. I know why you put me last, because I'm always talking very quickly. What? All right, it is spring at last. Yeah, spring at last. I wanted to show this to you because this is an area we're going to lose in the next few weeks. It's, well, I'll advance the slide there. It's Gemini region. This is, it's going down pretty quick. By the time we reach the next moonless window next month, you're not going to see this. You'll have to wait till next winter, right? Because you hadn't had enough of this one. Anyway, I just want to show you this because if you do get a chance in the next week to get out and have a look at this, this is still a very rich area of the sky. And you can see, if I just go back a bit here, you can see the winter Milky Way. Not nearly as prominent as the summer one, but still lots of nice targets in there, including things like the rosette down there. I'll just advance here again. So the thing I want to show you is actually tonight is between Canis Minor and Gemini, and continuing my series from last month where I showed you the Witch Head Nebula, my series of spooky women. Yeah, yeah. The Medusa Nebula, that's what I want to show you. So there's the Medusa. This is a planetary nebula about 1,500 light years from here, and it's quite large, but it's really faint. About 4 light years in diameter. That's a 4-hour exposure with the 11-inch scope and an SSPV2 CCD imager. It's very, very faint. You need probably Attila's light bucket to get a good view of that, if at all, plus a good collection of filters. But an interesting object, named the Medusa for the Gorgon Medusa because of the striated filaments, the braided hair. So, yeah. So the Medusa Nebula. The other thing I have to show you is in Leo, which is now coming to prominence, right? We're getting into spring, the time for galaxies. And the Leo area itself is a nice, rich area. Not many nebulas. Obviously, it's far away from the plane of the Milky Way, but you've got a lot of interesting targets to look at here. Targets that are suitable for binoculars as well as small scopes. There, you've got some very nice galaxies in the region there. So I encourage you to get out and check these out before we are hit by the moon again, and certainly next month when Leo will be nice and high, transiting around 11 o'clock or so, and before the sky gets too light as we approach summer solstice. So the thing I wanted to show you tonight in this area is actually down here. The Virgo galaxy cluster. There's not another part of the sky where you can turn a small telescope and see as many galaxies in one field or not. It's crazy. It is the Virgo cluster. It is the nearest galaxy cluster to us, and for aiming purposes, you don't even need an accurate mount. Just have a look at the nebula at the tail of Leo and Vendemeatrix in Virgo, and it's dead way center in there, and it's a large field. It's about, the Virgo cluster itself subtends about 8 degrees, so it's a huge area and contains well over 1,000 galaxies. So most of the things that you see here are the bright objects are galaxies. I've really toned down the brightness of the stars because if you sweep this area with a humongous set of binoculars or telescope, you'll notice the stars are a lot more prominent. These galaxies are relatively far away. The heart of the Virgo cluster is about 55 million light years from here. And the cluster itself contains, like I said, around, estimates range from about 1,300 to 2,000 galaxies. And it's part of the Virgo supercluster, which in fact our local group is being drawn to gravitationally. So we're kind of moving in that direction. But it's an impressive region of the sky just because, I mean, this is comparable to field of view in binoculars, roughly. But within this one field, you've got a tenth of Messier's entire catalog of objects. As you can see, they're all labeled here. And countless, I didn't bother labeling the NGCs and the ICs because you wouldn't see anything else. There's just too many circles here. But all these bright objects, yeah, they're all galaxies in this field. So I shot this with a 300 millimeter lens, giving me a nice wide view. And I want to have a closer look at this. This is my favorite area of this entire cluster. This is Markarian's chain. And it's just a spectacular grouping of galaxies with M86, M84, and M87 being the most prominent. But this chain is really remarkable, named Markarian's chain there. So that's it for the Virgo cluster. Hope you get a chance to check out some of these because even in a relatively small scope, you'll see a lot of galaxies in this area. They look like small smudges, but interesting to know what it is you're looking at. You're looking at the heart of the nearest galaxy cluster to us here on Earth. Thank you very much and good observing.
All right, thank you very much, Paul. So we are going to skip Observer's Challenge just because we're a little bit pressed for time. I'll email it out tonight, but you'll get a little preview there as I skip through it all. Try to burn this into your memory. I'm going to quiz you guys next month. All right, International Astronomy Day coming up on Saturday, May 11th. There's going to be an event here at the museum, daytime activities from 10 a.m. to 4 p.m. May also include outdoor observing of the sun and the moon and planets, and evening activities between 8:30 and 11 o'clock. Also a free public star party. If you're interested in volunteering, please reach out to Chris Tarrin, who is gracious enough to coordinate that for us. All right, here's a couple handsome fellas there. All right, and let's see. Oh, I think Jim Thompson was going to speak to this one. But please be brief if you can.
Okay, be quick. Okay. In the beginning.
So, like you mentioned, there's two main activities that happen on Astronomy Day. There's the activity that happens here at the museum, which is mostly sponsored by RASC because of the relationship. And then there's another activity. This is the 19th annual event held at the chapters in Silver City. It's on Ogilvie Road in the East End. And it's an all-day stargazing event as well. So solar during the day, switching to the moon in the afternoon. Maybe we'll catch Mars before it sets. We'll see. And then on to whatever we can see from a well-lit parking lot in the middle of the night. I really encourage people to get out and participate. It's such a great feeling to show children what the moon looks like through a telescope that they've never looked through, or even an adult who's never looked through a telescope before, just the amazement in their eyes. I'm sure Stu can attest to that. So yeah, if you're interested in coming to the museum to help, contact Chris. If you want to come to chapters, Silver City, you can talk to me, Jim Thompson. Right, thanks. Great.
Thank you very much. All right, moving right along, fellow star parties for members only. The next one is April 6th, which, if I'm not mistaken, is tomorrow, weather permitting. Estelle's pick of the month, the planets. Should be an interesting read. Our library is right behind me to my right. Here's some of the folks that help run the club. Thank you very much for your time and effort into running the club. As always, our meetings are recorded and available for viewing on our website. Thank you for coming. We had 115 attendees tonight. And thank you to all the organizers and speakers and to the museum for hosting us. There is a request from the museum that we do not linger in the foyer tonight, as they've got another event going on and they don't want us to interfere with it. So to that end, we will be having our post-meeting meeting at Grace O'Malley's as always, if you want to join in conversation and drink. Our next meeting, May 3rd, same time and same place. Any ideas? If you have any ideas for talks or observations to submit, you can send them to me at meetingchart@ottawa.rasc.ca. As always, there are various benefits for joining the club, so you can look into those on our website. You also get access to some great publications. And door prizes, I'll go through these quickly. I'll just read the last couple numbers there. Apologies for running so long. I'll try to do better next month.